We approach the beginning of the last session for the conference Electronics 2024, and it will be my pleasure to chair this session entitled Renewable Energy. That means session 10A. In the same time, I'm also first presenter for today, and I will open this session from this place. And immediately I will continue with my presentation. Thank you for attendance, and I will introduce myself, of course. Now, the first paper for today is Optimal Design, a Techno-Economic analysis of a hybrid system to supply a remote fish pond with electricity and heat. Authors are from my university, University of Pristina in Kosovska Mitrovica, and from Bulgarian Technical University from Sofia. Thank you. I have always problems with this. Is this here? This one more. Thank you. Oh, sorry. Sorry, there is the mine now. Now. What I can say in this introductory part, for example, this paper deals with a hybrid system composed of micro hydropower plant, photovoltaic generator, combined heat and power unit with one diesel generator, batteries, converter, and thermal load controller and boiler. For what is the novelty here? Inclusion of thermal load controller and boiler and field of application. This system without thermal load controller nowadays exists in eastern Serbia in one fish pond and produce trouts, only trouts. You know, trouts need cold water, and some other species of fish need a little bit warmer water. And our idea was from 5 ponds to share a production of fish in the same time to produce trouts in 3 ponds of them and in 2 carp fish. Carp fish need temperature, I think, about 16, 18 degrees Celsius. And this idea cannot be performed in practice without these 2 elements at the end shown, thermal load controller and boiler. That means we need production of warm hot water. And you can see there is located this fish pond, and our problem also is formulated like optimization problem. How to avoid the utilization of this generator that use diesel as fuel, because this fish pond is located far away from the cities and from the utility grid. And we need to have it like option. If we exclude diesel generator, this is completely green solution using electricity and heat produced in the one hybrid system composed of renewables. But location of the fish pond dictates that we must have as a reserve option this one diesel generator. In case to have cloudy days, night or somewhat, we cannot allow the temperature in the two ponds. There are carbs to be lower than 60 or 16 or 15 degrees Celsius. Now you can see classical objectives of this analysis. That means we have again objective functions, some constraints related to technical features, and now we have also economic part calculated up to the end. The simulations were conducted in Homer software, which is known for this kind of problems. And we got a unique optimal solution, which is in the same time economical, reliable, sustainable, and 90% green, not 100% green. On this slide, we can see some schemes taken, screenshotted from the Homer software. On the first one, you can see the main, not components that we cannot say for a micro hydropower plant that is component. But our hybrid system is composed of these 6 elements. And this is nowadays existing system. And what we did is shown on the right side of this slide. We included this thermal load controller and boiler to produce warm water for the growing up of carp fish. Also, like any home, any consume, and the fish pond has its own load diagrams. That means people have some rooms there they are living during production of fish, and there have light, heating elements, and other appliances which are listed here. And also fish pond has specific devices like oxygenator, cooling chambers, and so on. And all these devices and components needs electricity, or both heat and electricity. And we are talking about renewable sources. The main source of energy is sun energy, solar energy. And for this study, it's important to have some diagrams related to meteorological parameters like solar irradiance and clearness index and similar. One of the diagrams is shown on this slide, and you can see some parameters related to geographical coordinates of this existing fish pond, and some details related to the system shown previously on the schematic of this fish pond. The energy of water and micro hydropower plants is a little one, situated on Radovanska Reka. Some details about flow in this river, and some manual average and residual flows are given on the right side of this flow. And you can see that the average stream flow is the highest in April during the year, and that summer period up to the middle of autumn is with a small amount of water in this river. That means the river is very small, but away from the cities, away from pollution, and idea is to produce for the first time carp fish in the green conditions, good environmental conditions, because carp lives in, how to say, in rivers like Sava, Danube, which are contaminated, significantly contaminated. This idea was to produce the species from these regions, living in these regions in artificial conditions, but to get fish with clean meat, healthy. And also we consider the financial benefits of this solution. Some details, technical details and features related to components included in these hybrid systems are given on the next slides, and you can see a fuel consumption curve, efficiency curve for diesel generator. But without diesel generator, we cannot find the option to replace it, because always if you have some diesel in the reservoir, then you have need, you can use it. Components, converter, batteries, thermal load controller, and boiler are presented with this table shown in this side, and some details about them are given on the right side of the tables. And you can see efficiency, lifetime of each of components, and some technical details related to electrical parameters and so on. Also, and this optimization study cannot pass without tabulated details. And what is the main thing for this table? It outlines optimal configurations of the hybrid system. We didn't consider just one. We considered a number of options, and after that we selected the best one for this existing fish pond. On this slide, we can see environmental performance of the hybrid system configurations considered. Each of them is marked by ranks from 1 to 12. You can see this total emissions of greenhouse gases in kilograms per year, and also this fraction in percents on the right side of this diagram. I will also not go in the details. You can see green color are emissions, and this factor is shown in yellow color. Again, we have a comparative presentation for some of these configurations. And this diagram analyzes effects of renewable energy sources and thermal load controller on the system performance parameters. Summary of the costs for the individual components in the optimal hybrid configuration is given in this slide and some next slides. I will also pass through this quickly to be in the time of 15 minutes. For example, here we have electricity generation and heat production shown in this bar diagrams on the left side of this slide, and some technical performances shown in the tables on the right side of the slide. Now, cumulative discount cash flow over the course of the project lifetime is shown in this diagram, and you can see two curves. The first one in black is base case. That means composed of components listed in the parentheses, and proposed optimal hybrid system is presented by red curve, and that means this solution includes thermal load controller. That is difference between these two solutions. And at the end, we have conclusions of listed on this slide, and you can see that the optimal system configuration for the given case would contain components with given powers, and 109 batteries is needed for this, and also one thermal load controller of 39 kilowatts. The proposed hybrid system has the lowest total costs. You can see amount in US dollars, and also costs, levelized costs are, how to say, compared to other systems considered by us during this study, this is a little bit higher. This $178 per kilowatt watt hour. But if you aim to produce healthy and green food, I think this price is not so high, and this solution can be considered as economical and possible. Compared to the base case, the proposed hybrid system can reduce this net costs, levelized costs and emissions by given percents, and increase electricity generation, heat production by this process here. Integrating thermal load controller into existing hybrid system can reduce emissions and costs, and improves in general performances of the existing hybrid system on this considered Fishpond. And the proposed system is feasible because investment can be recovered after only 1.8 years. I think for green solutions, this one good period for get back all invested money. Thank you for attention, and now I will ask you, like a chairman and presenter, to ask me some questions and to continue this session. Welcome, please.
I have only one question. How big are those ponds, those Shuai ponds?
This ponds, this paper is already presented in the Electrotechnical Electronica journal, and details are given there. But a few times I was visited it, and some are in concrete, normal sizes. I think 4 or 5 meters with a few meters. We didn't measure that, but they have also one big pond, which is not with concrete edges and shape. And in this we saw some species different of trouts. And we found in this walking around the biggest basin, idea came to consider this option to change production of trouts with carp, because carp is only river fish that do not have so healthy meat. You know, because he lives in the mulj, kako se kaže? In mud. Lives in mud. Mud is not clear like previously 50 or 100 years ago. And this is the idea to produce carp fish to be healthy in this, how to say, polluted century. Thank you for question. Next one. Welcome, please.
Price of energy, 18 cents per kilowatt hour. What is the average cost of electricity in your country?
This is good question. We change price of electricity each 3 or 6 months. And for today's levels compared to other European countries, it comes that we have the lowest price of electricity in Europe.
Okay, thank you.
Thank you. Any more question for Chairman? Thank you to everybody. I will continue with my other task on this session. Thank you very much. The next presenter. The next presenter on this session, 10A, comes from China, and the presenter is Li Huang. I think this presentation will be through the cloud and the internet, yeah? The paper is entitled A Vine-Copula Method for Outlier Identification in Photovoltaic Arrays. Mr. Li, do you hear us?
Yes.
Welcome, please. Good evening or good morning. What is time in your country?
Can I start?
Yeah, you can start. Take your time, please.
Okay, thanks. Good morning, everyone. Now I will share our research titled A Vine-Copula Method for Outlier Identification in Photovoltaic Arrays. This work was done in collaboration with the China Electric Power Research Institute, State Grid Beijing Electric Power Company, and Southeast University. As PV technology grows, one of the main problems is finding and removing unusual data points that can affect how well the system works. Our research introduces a new way to solve this problem and make PV operations more efficient and reliable. I will quickly go over what we will cover. We will talk about the research background, current methods, our Vine-Copula solution, a case study, the results, and the possible future uses. Let's take a look at the agenda. Now that you know what we will cover, let's move into the introduction. Solar power is becoming more important in the world's move towards renewable energy. However, PV systems often collect data with mistakes caused by things like equipment problems, communication errors, or issues like shading or dust. These outliers need to be found and removed to keep the system running smoothly. Our research focuses on finding three main types of outliers: equipment problems, communication errors, and environmental issues. Solving this helps improve the efficiency and reliability of solar power systems. There are many methods for finding outliers in PV data. Traditional methods like the central limit theorem and the 3 sigma method assume that the data is normal, but often this is not true because of the changes in the environment. Machine learning methods like isolation, forest, and the local outlier factor also have issues. They can be unstable with different datasets and require a lot of computing power. This shows the need for a better, more adaptable method. To fix these problems, we proposed the Vine-Copula method. This method is flexible because it models how different variables like current, voltage, irradiance, and temperature depend on each other. It works in 2 steps. First, we found the outliers in the current, and then we move to the voltage data. We use the archaic information criterion to pick the best copula function, which helps find outliers while keeping the calculations efficient. Before we move on, let's quickly go over the key ideas behind the copula theory and why it matters in our method. Copula theory helps us model how different variables depend on each other while keeping their individual behaviors separate. This is important for PV data, which doesn't always follow normal distributions. Scalar's theorem is the key part of copula theory. It allows us to break down a multivariate distribution into its individual parts and a copula function that links them. This flexibility is important for our method. Vine structures help us organize these relationships. There are 2 main types: C-vine, which has one variable as the root, and the D-vine, which connects pairs of variables. In our research, we use the D-vine structure to model how current, voltage, temperature, and irradiance are related. This helps us capture the complex relationships between these variables. Each pair of variables in the Vine structure is assigned as a specific copula function. For example, we might use a Gaussian copula for relationships that are symmetric and a Clayton copula for the relationships that are not. We choose the best copula function by using the archaic information criterion, which helps us avoid overfitting and ensures the best fit. This is important for finding outliers accurately. Once we choose the copula functions, we can calculate conditional probabilities. This lets us see the likelihood of outliers for variables like current and voltage, given known factors like temperature and irradiance. Our method uses a two-step process. Step 1, we process the data, calculate the distributions for current, voltage, temperature, and irradiance, and find the current outliers. In step 2, we do the same for the voltage, using the clean current data for better accuracy. This step-by-step process allows us to detect outliers more precisely. Now let's look at some real-world data. We collected data from the Tungzhou power supply company between March and September in 2022. To test our model, we also added some fake outliers to see if our method could find them. In this table, we see how the relationships between current and the voltage were modeled using different tree structures. Tree 1 focuses on the strongest connections, and tree 2 refines these relationships further. Each edge in the Vine structure represents a specific copula function that captures the dependency between the variables. We used the archaic information criterion to select the best copula function for each pair. Below the table, the graphic representation shows how these relationships are connected, with copulas like C, Ig linking the variables. By optimizing these dependencies, we can accurately model the complex relationships in the data and improve anomaly detection. Our method reached a detection accuracy of 1960.5%, which is better than older methods like the quantile-based approach, which only got 73.3% accuracy. The plots show outliers in red and normal data in blue, which confidence confidence intervals. Our method also had a low false positive rate of 0.05. In conclusion, we introduced a two-step Vine-Copula method for detecting outliers in PV systems. This method greatly improves detection accuracy and works well for real-time applications. Going forward, we will work on making the model even bigger and faster for real-time use in large solar power stations. I'm happy to answer any questions or discuss any part of our research further.
Dear Mr. Lee, thank you for your presentation, but we cannot see you. Would you solve this first?
Oh.
Thank you. Any question for Mr. Lee? Of course, you will get question from my side if attendees do not like to ask you. The first one is, did you contrasted the proposed method Vine-Copula to other existing methods used in the field that you considered?
Oh, thank you. Question.
Did you compare the Vine-Copula method with other similar methods?
I don't have that information on hand, but I can follow up with you after the presentation.
Okay, thank you very much. Any
Thank you.
question? Thank you very much, Mr. Lee, for your presentation.
Thank you.
The next presenter is Professor Mario Vražić from Croatia, and he will present a paper entitled Current Control and Battery Pack Modules in Parallel Connection According to SOC.
Thank you, Chairman.
Welcome, please.
Well, as you said, I will not read this a long title again. This work, this paper, was produced by colleagues from the University of Zagreb and University of Maribor. Professor Petrovic is from University of Maribor. So, what is the background of this work? The background is we are working on electric vehicles. In the past, I did some designing of battery packs and electric vehicles. So we now have some projects with companies that are near the sea in coastal area of Croatia. So the idea occurred that we start to think about battery packs in boats, small boats, 8 to 10 meters. And if you have been on such boats, they are really very rocky, and it's not easy to enter to them and get out. And if you have the battery pack in one piece, so you will need to have outside some kind of power source, and there are limited number of places where you can recharge your battery pack. The idea is to have several modules which can be carried away, and so that you can build a battery pack with several modules that are not heavy and that are easily transportable. So you, let's say, dock at one place and just replace empty modules of battery pack which are easily carryable. Then we have some problems and of course ideas regarding direct connection of battery modules in parallel. So if you connect two modules or two batteries in parallel, you have problem with equalization current. So if there is a empty battery module and a full battery module, because of very low resistance, the currents are very high, and this is not good for battery packs. So right now, when you have battery modules in parallel, then you have actually only current limitators that are controlling the current and limiting the equalization current. The idea here is not to avoid any energy exchange between modules. So when you put a new fresh module in the battery pack, there should be no equalization current, but that balancing equalization should occur through load and regenerative braking over some small set of very simple rules. So those rules are, of course, when you have load and when you have several modules which has different state of charges, then when you have load, the majority of current flows from the module that has highest state of charge. And if you have very empty module, then its contribution is very, very low, very small. So you don't, so you avoid some damage of this module that is very low state of charge. So we come up with some, let's say, a system, but before that, we set up some characteristics or propose presumptions to that system or to that battery pack. So it obviously has to have scalability. You have to have several multiple modules. Since all those modules are in parallel, it's obvious that the total voltage of the system is the voltage of one module. And when you need to extend capacity of this system, then you add additional modules to the battery pack. Charging flexibility also, so the possibility that you at any point extract one or several modules and replace them with full ones. And of course, since everything is working according to state of charge of each module, so you have to have advanced and very smart state of charge control here. So we come up with something that we called bidirectional multiple input multiple input single output synchronous is something which doesn't belong here. That's what this is error. So this system is bidirectional multiple input single output DC-DC converter. How does it look? It looks like this. So here is an example of three battery modules in this battery pack. Of course, they're equipped with battery management system. This is BMS master, and this is that we come up to. So we have single output, to powertrain, to over DC-DC converter to motor or to other systems of the vehicle, and multiple inputs from batteries. So those are electrical connections, and this is communication. Of course, you can plug in charger whenever it's possible. So the idea is that from each battery module, energy flows in this direction, and of course, if you have regenerative braking, then it flows like this. But there is no exchange of currents of energy between modules. You can do it, of course, with the controller, with the smart measurements, so to avoid, because otherwise you have this current, and this current, if it's zero, then all the currents should be zero. And those converters should forbid the exchange of energy between modules. So all balancing is going through the load. This is a simple schematics of this model, but let's go to components of this module. So we have average a model of battery modules within this system. We have half bridge buck boost DC converters for each module. Why buck boost? Because if you, for example, here, if one module is a state of charge of one module is very low, so the voltage of this module is lower than this voltage. But if this one is fully charged, then his voltage is greater than this. So you have to have a buck converter if you are going up, and if you are going down, and boost converter if you are going up with the voltage or energy. Of course, some advanced but average model of current controller, and its PI controller, of course, for each module are made, and of voltage controller that oversees everything. So if you remember control systems, first is voltage controller, and it oversees and controls current controllers. And of course, we have to have state of charge comparison and current management script and system that runs actually everything. So we modeled this system in environment in software called Plex, and this is it's, of course, I will not go through this. It's not so important. And as we said, we used some average model of battery, but we say, okay, this is a battery cell, a battery module that has 28 cells connected in series and 6 cells in parallel, total 144 cells. This module has energy capacity of 12 what hours? I think not, but okay. This is something wrong with this number. Battery model has a nominal voltage of 100 volts, capacity of 20 amp hours, and energy of 2 kilowatt hours. And estimated mass of this module, 144 cells, again together with the carrying case and everything, is approximately 13 kilos, which is not so heavy, and you can carry it in one hand. So this was the idea of this. So we did in Plex simulation of tests. Those are not tests because those are not live and tangible things, but only simulations. And we had, for that purpose, we had 3 modules, each with different state of charge. So almost full, 90%, averagely full, and almost empty, 10%. So in diagrams, they will be represented by blue, red, and green. So blue is full, and you will see the rest, how it acts. So first, we carried out the test drive and regenerative braking. So we have a current of load, 10 amps, and then ramp up to -5 amps, and then to 0. So we did a lot of thinking how to do the best presentation of this phenomenon, let's say. And as we say, I will repeat, blue is the most charged component, most charged module. And as you can see, state of charge change. This is most charged module, and it gives most of energy. So the change of state of charge is the greatest for this module. And of course, this one is the weakest point here, weakest element. So the system tries to preserve it, tries to secure it, not to go to be broken. And the same here is the relative change. Still, you can see the point that I made. Then we have step responses. So step current plus 30 amps and -5 amps, like sudden load and sudden regenerative braking. And this is so from 0, now this is 0 current, and then it starts with 30 amps, and if you add those 3 currents of each module, you will have 30 amps. And the same is here when you add up those 3, it will be -5. So those steps, you can see battery voltage that, of course, the best charged module has the most voltage drop because he has the highest current running out of it. And this lower module has a very low voltage drop because it has very low current. And on the other hand, when there is regenerative braking, then this the state of charge of this is 10%, but current that flows to this module is the highest. So the things change depend of direction of current. This is just a magnification, so zoom of the 2 points. So we have this point here at 5 seconds, and we have this at 15 seconds. So next 2 diagrams are just magnification of those points. So we, as you can see here, this is this. Yes, this is when we change from 30 amps to -5 amps. And as you can see here, what happens, this is the most charged module, and current flows to 0 and approximately stays to 0. And this is the weakest module that has the lowest load, but the highest charging current. And this is something that we want to achieve. And of course, this is at point of starting high currents of 30 amps. So 5 seconds, at 5 seconds, where you can see how the modules, distribution of load to the modules, and of course the blue module receives the most load, which is intentional. And fast conclusion. So we start to think about this and starts to doing it, and this BM-ISO structure was actually something that we come up during this process of designing and thinking. We did some basic simulations just to test the current controllers. The current controllers are here very important to avoid, especially at those points of transition, to assure that current flows are very smoothly, that you don't have any shocks to it. As I said, current management is here very important. And of course, with balancing, almost everything here is programmable. So you can choose what kind of strategy of balancing you can use. It's not difficult to change the strategy depending the battery characteristics. Are they acceptable to high currents of charging or discharging or not? So you can do a lot of interesting research regarding components that are inside this system. And of course, further research, as I said, is possible in a lot of directions here. Well, thank you very much.
Thank you very much for your presentation, Mr. Vražić. Any question from your colleagues? Any question from please?
Hello, thank you for your Yeah, hello, sorry. Thank you for a great presentation. Can I ask you, how do you manage to power the MOSFETs in your battery module solution? Because if the battery drops below some certain point,
Yeah.
those MOSFETs wouldn't work.
Yeah, but there will always be a module that is working,
Oh,
and you have a battery management system that does not allow battery to go to voltage zero. So battery management system will block batteries from giving away energy because to the load, because it has to preserve batteries. That's why when you're having when you let's say driving electric vehicle will stop at one point, but you will still have some systems running, but current controllers will stop high currents discharging from batteries.
Yeah, thank you.
Yeah, you're welcome.
Thank you for your question. One more question we have for Professor Vražić.
Thank you for your presentation. I have a question. If there is any prediction you could make about the impact of this management system on the battery life, would it increase or decrease each battery pack life?
Well, this is very important question, and I think nobody had a nice answer to it except to do a lot of experiments and see it. Because we all know battery cells. Their optimal working conditions are from, I don't know, 20% of state of charge till 80%, and you should use it in that period. Okay, so if you are doing from 50% till 80%, they're even better. But the number of chargings will increase, and each battery has a maximum number of cycles. But what cycles? From 20 to 80, from 50 to 80, so we have that problem with the batteries. But so far, let's say 10 years or almost 12 years ago, I did with my students one Opel Kadett old car, and we converted to electric power. Batteries from there, and now they are almost 3 times better. Now batteries 3 times more power and energy density in battery cells than then. So 10, 20, 12 years ago. So I expect that this technology of batteries will come up to the solution of this. But right now, when you buy a new electric car, you have, I don't know, 8 years of warranty for batteries. But nobody says, will you buy 8-year-old car electric? So this is the problem that will probably have to be solved within 8 years or 10 years.
Okay, thank you.
Welcome.
Thank you for question. Any more question?
Yes, very interesting. It's very interesting presentation and work. But tell me, have you already found the foundations? And if yes, where?
Funding?
Yes.
Well, I work a lot with industry.
Yes.
And then I didn't pay that money that I earned to myself. I invested in batteries and in such systems. Okay, and recently we had a nice, very big project that a faculty of mechanical engineering, my faculty, and a private company had funds comes from the state, and we managed to build from scratch, designed and build 2 minibuses. that are up to 5 tons. And now they are in the testings. This is a 3-year project. Now it's in its 4th year. And, you know, you managed to come up with ideas and funds in different ways. We manage, we are engineers. Yeah.
Thank you for your question. And you will get one question from me. Did you try to implement, consider a current control system in laboratory conditions?
You mean made from
Yeah,
live components?
Yeah, live component.
Yes, but we're still not finished. This is the beginning of the presentation for the beginning of the project, and right now we are working on it and try to solve problems which are more advanced than this.
That's all from my side. Thank you, Mr. Vražić, for your nice presentation and good paper.
Thank you.
You're next presenter comes from China, and I hope also we will make connection with presenter. The next presenter is Tangyong Teng from China, and he will present the paper entitled "The Risk Assessment Method for Distributed Power Distribution Networks Considering Network Dynamic Reconstruction." Welcome, hi, and
Hi.
take your time and present your work, please.
I know. 整个屏幕。哎，这怎么弄啊？Sorry，
Sorry, something is wrong.
Could you unmute your microphone, sir, because we cannot hear you.
Oh, I'm sorry.
Now it's okay. Start, please.
Okay. Hello, everyone. Today I want to show the topic of risk assessment method for distributed power distribution networks, considering network dynamic restriction. My report is divided into 4 parts. Part 1, introduction. We will discuss the background, the changes of traditional risk assessment methods, and our proposed solutions using dynamic reconstruction and efficient simile techniques. Part 2, what did we do? Here we provide a detailed introduction to our research, including distributed generation models, system, and photo state model. Distribution network reconstruction model, risk assessment process. Part 3, case study. Part 4, conclusions. Okay. Part 1, introduction. Background with the advancement of China's dual carbon strategy, the penetration rate of distributed power sources such as wind power and photovoltaics in the power system continues to increase. Wind power and photovoltaic output are greatly affected by factors such as weather and with significant uncertainty result in difficult in ensuring the sustainability of power supply. With the increasing uncertainty of distributed power sources, distribution networks are facing more risks, and there is an urgent need to conduct risk assessment to ensure safe and stable operation in the event of force and extreme station. In the above context, the risk assessment of destruction networks will face the following three major challenges. First, the exciting static risk assessment methods cannot consider the dynamic reconstruction of destruction network after force, ignoring the reliability and photo recover capability of system components. Second, traditional Monte Carlo methods have high computational cost and low efficiency. When dealing with large-scale samples, making it difficult to meet the need of risk assessment for complex systems. Third, traditional single indicator evaluation cannot fully reflect the risks and of voltage, power flow, and load loss in the distribution network. To address this, to address the first challenge, we proposed a dynamic risk assessment mode that incorporates a distribution network reconstruction model combined with the output prediction of distributed power sources and the reliability of system components to enhance the ability to recover from force and the safety of system operations. As for the second challenge, we use Haitao sequences instead of Monte Carlo methods to reduce the number of samples, improve communication efficiency, combine analytic hierarchy process and entropy weight method comprehensively evaluate the risk of voltage, power flow, and load loss to make the evaluation more objective, and analyze the impact of distributed more power sources, location, and capacity on system risk. Part 2, what we do. What did we do? Next, we will discuss the modern method of distributed power generation. Web distribution is commonly used method for the window speed modeling, which can simulate changes in wind speed. For photovoltaic output, we use the beta distributor. Finally, for the load model, we use a normal distribution to model the volatility of the later. This page displays the system feature state model. Firstly, for wind turbines, we calculate their forced outage rate and probability of failure status. The formula here demonstrates the relationship between failure rate and repair rate. The forced outage rate and failure probability of photovoltaics modules as well as the probability of line failure status are similar to wind turbines. Here the reconstruction model is constructed with object function of minimization, network active power loss, which is subject to the following constraints, including power flow constraint, voltage and current constraints, connectivity constraint. In the constraint conditions, we adopt two key relaxation constraints. First is the big M themed method, which includes sufficiently large constant M to relax to the on or off status constructs of broaches. Secondly, we use second order current relaxation, a technique for handling non-linear constructs. It transforms the non-linear contracts of power flow into a more easily slowable linear form. Part 3, case study. On this page, we discuss two components of risk assessment evaluation metrics and evaluation modes. Firstly, the evaluation indicates including voltage violations, power flow violations, late shutting. Next is valuation method. Here we use a combination of entropy weight modes and analytic hierarchy to determine the final vice. Multiply the risk value for a certain set by this probability, and then sum up the results abandoned for all states to abandon the comprehensive risk variable of the system. Here we demonstrate the connection of wind and photovoltaic system at different nodes and capacities, and analyze the system risk values. Firstly, the value on the left is the risk values of multiple line for force in the IEEE 13.3 bus system. Node 4 and 6 are the front-end postations of the system. Nodes 11 and 14 are the middle postation, and node 17 is the end postation of the system. It can be seen that as the capacity increases, the risk value of the front end and middle nodes are low, where the risk values of the end nodes significantly increase. The same applies to the IEEE 118 bus system result. Finally, we draw an important conclusion. Larger capacity distributed power sources should be connected to the front end or central postation of the system, where small capacities can be connected to the back end of the system. Verify the efficiency and accuracy of the sequence Hutton sequence most used. The molten color mass is used as a compare window turbines and photovoltaics with capacity ranging from 200 kilowatt to 800 kilowatt are connected to nodes 11, 14, and 17. Table 1 shows a comparison of the risk values obtained by the two sampling methods compared to the MC method with 10,000 sets of samples. The Hutton sequence sampling method with 3,000 sets of samples is used, and the time record for the case study is 15% to 16% of MC, with a maximum error of only 2% compared to MC. Next, to validate the risk assessment method.
Sorry for this break. Could you conclude your presentation because time is over? Just conclusions.
I'm so sorry. Okay. Then part four. 行。 Then next the part 4 conclusions. Regarding the issue of security risk assessment in distribution networks, this paper proposed a method for security risk assessment in distribution network with distributed power sources. Take into account line reconfiguration. Case study have verified its effectiveness, and the conclusions are as follows. Large composite distributed power sources should be connected to the front or middle of system, while smaller capacity can be connected to the end of system. This assess most help reduce overall system risks and improve system reliability. After user harden sequences instead of molten colors, most the simulation communication time was reduced by 13%. This proves that the simply math improves communication efficiency, where molten evaluation accuracy. By using numerous start samples, this method provides a more comprehensive risk assessment considering both safety and reliability, and it's more effective than traditional static assessment. My report is over. Thank you.
Thank you, Mr. Teng, for your presentation. And we spent all the time. And we must continue with the next presenter. Thank you very much. And
Thank you.
And the next presenter comes from Turkey. I can Bolugbasi is here. Oh, online.
I'm here. Hello.
Hi, welcome, please.
Hello. Greetings from Turkey.
Yeah, take your time and present your paper, please.
Okay. We are pleased to participate in electronics conference. Hello, everyone. Our study is hybrid renewable energy production scenarios using long short-term memory method, a case of study of Göksu. Energy has been important part of our lives since the beginning of humanity. As civilization and technology develop, the demand of energy has also increased continuously. Fossil fuels have been important source for energy production since industrial revolution. Fossil resources have limited reserves. They have very harmful effects on nature. Their production costs are high, alternatives are needed. There are many studies being carried out in the world for the use of renewable energy sources in production. Energy production with clean sources is very important for humanity. In this study, it is aimed to improve technical, economic, and environmental parameters with hybrid renewable energy source system configuration to meet the electricity load demand of Göksu district, which is 40 kilometers away from Afşin Elbistan thermal power plant. A hybrid system was created in optimization scenarios using the Homer program. By making economic analysis, sensitivity analysis was made for inflation values and emission values were also calculated. Load estimation was made with LSTM, a deep learning model widely used in the analysis of time series data. With the estimation results, an economical and eco-friendly applicable energy production model that will meet the electricity demand on long-term was proposed. You can see the hybrid system schematic in our paper. Is conclude PV panel, electricity, user, inverter, and meters. All of them are connected with each other. We are using in our study Homer program. You are seeing the Homer's interface. Homer hybrid optimization of multiple electric resources program using more than 250,000 users. Homer is one of the most important programs in the field of design optimization and feasibility. It is an easy interface for designing and optimizing hybrid energy system connected to grid or independent from the grid. It is a micro power program that can calculate the sensitivity and cost of different parameter combinations. And then you are seeing our model design of using Homer, modeling PV photovoltaic system, modeling and of battery system and inverter. We are using these formulas to calculate our output. Economic and environmental parameters are, first of all, cost of energy. It is ratio of the total annual cost of the system the power is provided the same period. Cost of energy calculation is found by dividing the annualized total system cost by amount of AC and DC load pair and amount of electricity sold off the grid. And then the net present cost is, it is value of project discounted at the real interest rate for all future cash flows. Provides information on how profitable the project. The calculation of the net present cost is found by dividing the analysis system cost CRF by the capital recovery factor. Here, I is the real interest rate. Our project is real project life. In addition, Homer can also calculate emission values that are harmful to the environment. These can be listed as carbon dioxide, sulfur dioxide, and nitrogen dioxide. I now turn the speech over to Dr. Habibe Karayip, an expert on LSTM method, who will explain the methodology of this study.
Hello. In our study, we utilized electricity consumption data from the Göksun district of Maraş city within the borders of Turkey. In the data processing phase, underwent several processing steps: data input, data indexing, handling missing values, adding month information, data normalization, and preparing the dataset for time series analysis. In the modeling phase, we used various machine learning methods, LSTM, SVM, CNN, LSTM, GEO models. The parameters of these models were determined using a trial error method. In the LSTM model table, LSTM model have 3 layers. First LSTM layers 512 units. Second LSTM layers 512 units, and last layers, third LSTM layers 256 units. We determined for values trial error method. First 2 layer return sequence true. Last layers have return sequence false, and dropout and L2 regularization enabled in the LSTM model. In the SVM hyperparameter table, the RDF kernel function was preferred and the C parameter was set to 10, while the epsilon parameter 0.1 value. And hyperparameters of the Giro model table. Giro model have 2 layers, and first Giro layer is 200 units. Second Giro layers have 100 units, and first layer return sequence true, last layer false. Dropout and L2 regularization used for this model. CNN LSTM model have 2 layers. First layer 1D layer, and second layer LSTM layer. COM1D layer have 64 unit, and the second LSTM layer 50 units. Kernel size 2 we used, and the dropout rate enabled, and all deep learning models used dropout rate and its value 0.2. We use dropout layers and L2 regularizer for to prevent our model from overfitting. In the training and forecasting phase, 80% of the data was used as training set, and 20% data for the test setting. The month information was digitized using the one-hot encoding method and added the model's inputs. This method allows the model to learn seasonal effects of the months. In the evaluation section, various performance metrics were used to assess the success of models. Statistics were recorded Excel. Programming and visualizations related to the predictions were created. The graph compares the electricity consumption data from 2019 to 2024 with the predictions made using various machine learning models. On the graph, actual electricity consumption data is represented by the blue dots, and the model predictions show in the different colors represent the result of different models such as LSTM, Giro, CNN, LSTM, and SVR model. As can be seen, all models significantly overlap with the actual data, indicating that models effectively capture seasonal and trend-based fluctuation in electricity consumption. As seen in table, forecasting original demand table, various performance metrics were used. These metrics include RMC, MAPE, and R squared. In the light of these results, load forecasts made using the LSTM model. You can see LSTM model and model achieving the lowest may to other model, LSTM achieving lowest may RMC and MAPE, and as well as the highest R squared value. In the light of these results, load forecasts made using the LSTM model were simulated using Homer Pro software, resulting in the design of the most suitable hybrid energy system. Homer software is capable of processing economic, financial, meteorologic data, components data, It takes prediction data as input, and determines the optimal parameters using a grid search algorithm. It performs simulation and optimization processes, and after the optimal configuration settings, it calculates emissions, minimum net present costs, and the cost of electricity generation. Or estimate outer pattern, I can represent the result obtained with Tomovic.
And then we are seeing this simulation from Homer software program. In the upper left corner is this area. We see the schematic structure consisting of the electrical grid, Göksun load, converter, PV panel, and battery. In the upper right corner, we are seeing the monthly average electricity production graph. Orange color indicates electricity grid production. Green color indicates PV panel production. There may be differences in production according to seasonal changes. The table below shows the outputs of scenarios according to parameters and cases. Case 1 shows this area. Case 1 shows the base system. The current state of Göksun in the year 2023 is output. Cases 2 and 3 shows the outputs obtained with the estimated load generated using the LSTM method. In case 2, there are 3 scenarios for year 2026. The first one is the PV panel production output of 4 megawatt. The second is the production of 6 megawatt. The third is the output of 8 megawatt production. In case 3, there are 3 scenarios for year 2028. The first is PV panel production output of 4 megawatt. The second is 8 megawatt production, and third is the 10 megawatt production. As a result, the use of renewable sources increases in electricity generation. The cost of energy and environmental harmful gas emissions have clearly decreased. And then on the left, we see the surface graph by year created as a result of sensitivity analysis of Homer program. The correlation between annual electricity production and carbon dioxide emission. When the scale values of surface colors in figure and examine, it is clearly seen that the amount of carbon dioxide decreases as PV production increases. Finally, on the right side, this area, cost of energy values are calculated according to 0, 4, and 8% inflation rates for each year. In all graphs, the effect of increase in the inflation rate on the cost of energy value is shown. As the inflation value increases, the electricity sales price also increases. The negative results of increased inflation are shown. I now give the speech turn to Dr. Habibe Karayip to explain the conclusion section.
Conclusions. In the results section, we have extracted the following items as conclusions from our study. 1, LSTM model performance. Out of the model used is in our study generally performed well. The LSTM model achieved the lowest May RMC and May values and the highest R secured value. Constitution differences. The earthquake that occurred in Turkey in 2023 created the largest disparity between the models' prediction and actual conceptions. Used dataset models may achieve different classification success when applied to larger capacity datasets. Hybrid power system, the forecast result obtained in our study can be used as a valuable input for the design of hybrid energy system for the Göksun Street. Fifth, photovoltaic power generation. 6, cost of electricity generation. 7, carbon dioxide emission. In response to the increasing load demand, the values of carbon emissions released into environment have been reduced. Also, the inflation values have also been reduced.
On behalf of everyone who participated in this study, thank you for your listening. Our presentation is finished.
Thank you, Mr. Aykan and Mrs. Habibe, for your presentation. You presented good paper. Any quick question for our colleagues from Turkey? It seems that there are no questions.
Okay, thanks.
Thank you very much and goodbye.
Goodbye.
The next presenter comes from Lithuania. She is Živil Vilkelite. I think my pronunciation was correct. And she will present paper, a review on convolutional and recurrent artificial neural networks for the smart grid applications. Please take your time and present your paper.
Hello, can you hear me and see the slides?
Yeah, we can hear you. Please start.
Hello, to begin with, I'm Živila Vilkelita from Vilnius Tech, and I would like to introduce my colleagues that as well contributed to this work. First of them is my PhD thesis supervisor, Jonas Vanagas, Mr. Saad, Dr. Karabakh, and Dr. Jamil from different universities in Morocco. And last but not least, two professors, Professor Bojan and Wojciechowski from Poland, University of Radom, that I had an opportunity to do my internship with. Regarding the topic, the integration of artificial intelligence and machine learning technologies into critical infrastructures such as smart grid for load forecasting and enhancing the system stabilities has raised significant concerns regarding the cybersecurity. This presentation shows the dual role of AI and ML in both enhancing and challenging the grid systems. By analyzing state-of-the-art research and technologies, the utilization of both of these technologies to fortify defenses while addressing vulnerabilities is presented. For this review, two artificial neural networks were taken into account. First of them is convolutional neural network, and the second one is recurrent neural network, as well as their hybrids. Since CNN is widely used for image analysis and specializes in detecting patterns and link them together in the way they would make sense, it was used, and this is the basic structure of such neural network, whereas the recurrent neural network is used to process sequences. They are used for applications where input and output data sizes are variable. Thus, RNN captures different setups of input-output data in a model, and the basic structure is illustrated in the picture below. Regarding the learning types, according to the literature, it is stated that there are four main ones. When learning and testing data all together with solving regression and classification issues, that is all part of supervised learning. Reinforcement learning is utilized in situations when testing and learning data are unknown before the learning process. For tasks that involve grouping and association, unsupervised learning is employed, in this case, while testing data is readily available and it cannot be distinguished from the whole quantity of data. The learning data is not labeled as well. In the case when learning data is accessible and partially labeled and testing data is available, the semi-supervised learning method is used. It is employed for specialized mixed tasks of supervised and unsupervised learning that enable a prompt learning process. Regarding the cyber attacks, The literature considers three main ones regarding the grid technologies. The first one would be the man in the middle, and it is considered to be successful once the link between the client and the server is it is interrupted by a perpetrator. Another typical hack that is used to cause the distributed denial of services, it is a botnet attack. Several devices have to be enlisted in this type of hacking. And last but not least, fake data injections, as an example, is illustrated here. It is considered to be successful as soon as perpetrator connects to one or more than one Internet of Things devices that are in the system. In this case, cyber attack is dangerous as it could target the whole system or just parts of it. Figure illustrates the fake data injection into here. Valid data set is exchanged by the fake one, and the whole machine learning algorithm is corrupted. Further, where about the power stability and where artificial intelligence could be used to guarantee that consumers receive a reliable power supply. The stability of the power system is essential. It is considered to be from three main things, that is voltage stability, frequency stability, and transient stability. As the amount of renewable energy increases, problems with these 3 points appear, and the load forecasting is used to more precisely plan the load of the system, and AI networks could help to do this. An accurate forecast for every time period is more difficult due to renewable energy sources. Owing to the unpredictable characteristics of renewables, such as wind and solar, extra precautions shall be taken into account to predict the load of the power system. AI is gaining traction in cutting-edge research on enhancing power demand forecasts. Since smart grids, Internet of Things, and fifth-generation Internet become more and more widely used. And this illustration shows the time intervals that load forecasting could be done for. So short-term, for minutes to hours, mid-term, for hours to weeks, and long-term, for weeks to years. Many variables have to be taken into account to create an accurate short-term forecast, including meteorological data, power consumption data, patterns on hourly basis, market price indicators, and random events such as illnesses and, I don't know, natural catastrophes. In order to guarantee power system stability, midterm forecasting is employed to ensure balanced power system. Such forecasts are used to plan the generation of power grid units and to schedule maintenance on the power grid systems. Regarding the long-term forecasting, it is done in order to plan the infrastructural changes, and this forecast guarantees the accurate future power demand. It could be used to assess the cost associated with electricity transaction and distribution in the system. And when it comes to load forecasting, AI-driven models like CNN show impressive potential for increased prediction accurately over the range of hours power systems may more effectively anticipate and adjust variable demands of renewable energy sources by utilizing artificial intelligence, which improves the overall grid resilience and optimizes resources allocation. The research presents such results. These would be the 3 bullet points. And the use of the AI to improve power system stability highlights technology ability to lessen the stabilizing impacts of integration of the renewables. The power grid could more effectively regulate the stability of the system, as shown here. And AI enables fault detection systems, significantly improve the safety and dependability of the power grid. System equipped with AI have the ability to quickly detect and handle abnormalities like malfunctions, short circuits, which may reduce the downtime and increase the operational efficiency. As illustrated, the accuracy of using AI, particularly convolutional and recurrent networks, is illustrated here. Thank you for your attention. Maybe you have some questions.
Mrs. Zivile, thank you for your nice and interesting presentation. Any question from your dear colleagues? Welcome, please.
Thank you very much. I really enjoy your presentation. I like it very much. And I see the structure, you know, it's perfect almost. My first question is related to the review. How many literature you have foreseen, you know? And where
let me check to be precise.
I only ask it because the title is review. You know?
Yes, it is a review. It is a short review.
Yeah.
And
roughly 40, 60.
Around 50 for this one, I believe. Yes.
Oh, thank you. This is okay. That was a key issue, you know, because
no, it's definitely not 3 or 4. No, it's far more.
Okay, the second, what you explain it here, it's very similar for my subject, what I in the institute, I'm professor in it, is a cyber physical system, you know. Most likely you heard about it. It's everything constant. After that, we have so-called Industry 4. And today we in the Industry 5, where the artificial intelligence or the next generation or extended cyber physical system is included. And there are many, many different areas, even more than you mentioned. And one of them is the cyber security. You know, not only the cyber attack, because we have problem with the malfunctioning of the system. And you can detect it, you know, as a cyber attack. Basically, if something happens with your power supply or something. And also, I can imitate a cyber attack or make a real cyber attack, and I cover it like, you know, malfunctioning. So I think maybe it makes sense somehow look after the cyber physical system 5.0 or industry 5.0 and see all of the picture together, you know, because otherwise, you know, using artificial intelligence, it's very good, very smart one. I congratulations. And also the danger to mislead, and it's key point of your findings, mislead this artificial intelligence managed system is also very high. Thank you very much.
Professor, thank you for your answers. And I have also one question, or maybe it's better to say direction for your future research. Take care about criteria, how you select papers for your review in the future. This is very important, not only number of reviewed papers.
The number of reviewed papers I just checked was 84 to be precise.
Thank you very much. Any question for Mrs. Živile? No. Thank you very much for presentation and answers. And came the time to conclude this session 10A. We had 6 papers in this session. Presenters, we had 7, because 1 paper was presented by 2 persons. And I think that we were successful today. Thank you to our hosts, to attendees, and all colleagues online, and you who are here. Thank you.